so we're going to start talking about concavity. So slope tells us the rate of change of the original graph, the original y. Concavity tells us the change in the slope. Which, if you're thinking of it in physics terms, which we will do some of, is acceleration. So concave up means the slope is increasing, which means f prime of x is increasing, which means f double prime of x is positive, and that u, so the concave is really fortunate that up is spelled like that, because in the original graph it looks like a U. So if you kind of like draw, you know, the surfboard, when we talked about like a tangent line, there's that surfboard. I showed you guys the surfboard. Straight edge. So, like if I were to draw the tangent line right here, I'd kind of have, you know, like that slope to it. So, what concave up means is the slope is increasing as I go from left to right. So right there, would you agree that my slope is negative? As I go left to right, would you agree that my slope is less negative? Isn't that increasing then if it's less negative? Like my bank account was negative $10, now it's negative 5. Well, I'm making progress, right? I'm increasing. Now it's 0. Now I'm break even now. I'm racking up the dough now. So it's still increasing. So now it's like slightly positive, and now it's more positive. So that's what concavity means. The slope as you go starts just tilting more and more and more up. And concave down is the opposite of all that. And concave down, you got that N at the end, and that's the shape that makes. So it's kind of nice. So slope is decreasing, which means f prime of x is decreasing. F double prime of x is negative, and you get that shape. So starting tomorrow, we're going to be putting like the first and second derivatives together, and that's basically a summary of what we're going to really try to get you to understand, both on a graph and an equation, all the stuff over there. But today we're just going to worry about concavity. So we're going to do a very similar process to what we did to find relative maximum. So let's say I gave you 1/6 x to the third plus x squared plus 3x. And I'm going to say finds concave up, concave down, and points of inflection, which we'll talk about in a second. So the first thing to realize is that tells us to go to the second derivative. So that's kind of your first job. You're going to be asked to find those things extremely often. So increasing and decreasing, you go to the first derivative level. Concave up, concave down, you go to the second derivative level. So you can take the derivative in your calculator at this point. I don't care about that. It's fine. And this one I think it's just as easy to do it by hand, but that's all I have to do. I'm not gonna, I don't care how you get to it. Just get the second derivative. So if I'm doing the first derivative, 3 times 1/6 will be 1/2 x squared plus 2x plus 3. And if I wanted increasing, decreasing, relative max, relative min, I would stop here, so that'll equal to 0, and work with that level. I'm not asking you about that in this one. We're kind of skipping through that. I'm asking you about concavity, so we're going to go a level down to get to that information. So now my derivative would be x plus 2, the second derivative of the first. And the exact same process you did for relative max and relative mins, you're going to do for second derivative. So you can set equal to 0, top and bottom equal to 0, get your critical points, make your number line, plug back in. Now what level are you going to plug back into now? Plug back into the level that you came from. So you're going to plug into the second derivative, and that's going to tell you concavity. So set this equal to 0, and if there were a bottom, you would set the bottom equal to 0 also. So I get x equals -2. So set up a number line. Put -2 on there. And that gives us our intervals. -infinity to -2, -2 to infinity. And then same as before, we pick a point from that interval and we plug back into the level we came from. So because this came from the second derivative, I'm going to plug back into the second derivative. So pick like -10, let's say. Plug back in there. So it'll come out negative or positive. Negative. So this is f prime is negative, which means f is concave down, and on my number line, I'm going to write it, I'm just going to put it down here. So what I'm going to end up doing, because we're going to have to summarize all this eventually. On the top of the number line, we're going to write whether things are increasing or decreasing. On the bottom of the number line, we're going to write whether they're concave up or concave down, and it'll give us like a little snapshot of kind of what's going on in the whole graph. Alright, so for the second part, plug in, say 0. 0 is between those two numbers. 0 plus 2 is positive, so the second derivative comes out positive. So f is concave up. And if it changes, that's a point of inflection. So a point of inflection is where the graph switches from concave up to concave down. So because I switched here, I have a point of inflection. At -2, comma. Where do I plug back into to get the y value? So that's another thing, the original tells us y value. So if I plug in -2 to the original, -2 to the third is -8. So it'd be like 8/6. -2 squared is 4 minus 6. So that's, I'm not too concerned about this number. In fact, I'm just going to stop. Do you guys know how you would find the y value? That's all I need. Questions on any of the rest of it, though? I'm going to do a couple more, but let's take notes on that point of inflection too. Point of inflection. H is a change in concavity. So the second derivative changes signs. And what that looks like is something on original. It could look like this, or like this. Like if I'm looking at this one, can you see how it's hard to pick out like the exact spot? But hopefully you can see a general area. Can you see how this starts off looking like an N, like it's bending downwards? But then over here it flips, and now we're curving upwards. Look how it changes. So that point of inflection is probably about right there. I mean, we can use math to find exactly, but I just sketched this, so we're just kind of looking. Okay, it was curving down, and now it's curving up. Where did that change? Same thing over here. Right here, are we concave up or down? We're concave up, and then I flip, and all of a sudden I'm concave down over here. So somewhere in this region here, there was a change to when I stopped bending up instead of bending down. That's point of inflection. Questions for me at all? Where is this coming from? What are you doing? What's going on here? Alright, let's do another example. Let's say x minus 2 to the 1/3. And I just said find where it's concave up, concave down, and points of inflection. So I did not ask you to find relative max or relative min, so we can skip through that first derivative level. Let's review are there any asymptotes in this? No, why not? It's not a fraction. And again, you could do the derivative in your calculator, or you can do it by hand. It doesn't matter to me. I'm just going to do this by hand because to me that's easier than getting my calculator out. But it could be different for you. So I bring the 1/3 down, leave the little guy alone, reduce the power by 1, multiply it by 2. So this is really like 2/3 times 2x minus 2. Negative 2/3. And so the second derivative, when I bring the negative 2/3 down times this 2/3 would be negative 4/9. Leave the little guy alone. Reduce the power by 1. Multiply by the derivative of the inside. So I really have negative 8/9 times 2x minus 2 to the negative 5. Questions on what I did there? And again, you can type in your calculator, like I have no issue with that. Now your job is set the top and bottom equal to 0, so you need a top and a bottom. So I have negative 8 on top, and then 9 times 2x minus 2 5/3 at the bottom. So set the top equal to 0. Well, that never happens. Negative 8 equals 0 is nothing. Set the bottom equal to 0, and then this is where it's really nice that everything just kind of goes away. So basically, this is just 2x minus 2 equals 0. Because the 9 will cancel when I start doing stuff with the 0. The 5/3 will cancel. It's just 2x minus 2. So I get x equals 1 as my critical point. What's next? What do I do with that critical point? It's a critical point. It may be a point of inflection. I don't know yet. It's a potential point of inflection. What do I do with the 1? Stick out a number line. Then what? Label the intervals. And I'm going to pick a point from each interval and plug back into which level? Second derivative. You plug back into the level that you came from. So like if I pick 0, so again, think through the positive and negative aspects of this. I don't care what the number is. I'm going to plug, well here, let's plug 0 into this second derivative. 0 minus 2. Positive or negative? Negative. Third rooted. So if I'm doing something to the third power and I ended up negative, how did it start? Started negative. Now do that to the 5th power. So 5 negatives is still negative, right? Because 2 of every 2 cancel out. So I'm still negative. Now I multiply by 9. Still negative. But negative divided by negative. Now I'm positive. So the second derivative is positive, which means what is true about the original? not increasing necessarily. We don't know that yet. It's concave odd. And so I would go up here and just put like a little up. Same idea for the 1 to infinity, so pick like 10, let's say. Plug it in here, 2 times 10 minus 2 is positive. The third root of a positive is still positive. To the 5th power is still positive. Times 9 is still positive. But then a negative divided by a positive. So now f prime comes out negative. So f is concave down. So do I have a point of inflection? I do, because it's switched. I'm concave up here, I'm concave down here. So I have a POI, point of inflection, person of interest, at 1 comma, and where do I plug back into to find the y value, the original? So I plug 1 in here, 2 minus 2 is 0, and 0 to any power. So this is just 1 comma 0. Questions on any of that? Okay. Let's do one more, but I'm not having you do more than I do here. I also want to show you how to do this in the calculator. So y equals x squared over 2x minus 4. Get your calculators out if they're not already. So you can actually skip right to the second derivative on here. I mean, you could, if you really wanted to, you could take the derivative. There'll be times when you want to do this too. Take the derivative and then tell the calculator to take the derivative back. But you can skip to the second derivative. So if I want to do the second derivative here, I'll F3 Calc, differentiate, type in our equation, so x squared divided by, I'm going to put that 2x minus 4 in parentheses because I want to divide by the whole thing. And then hit comma x because that's the variable we want the calculator to use, and then hit comma 2. And so what this is saying is take the derivative of this equation, use the variable x, so take it in terms of x, and take the derivative twice. So it'll skip down to that second derivative level for you. It just saves you a little bit of time. So 4 times x minus 2. 4 over x minus 2 to the third. This is why we're using the calculators. Because we can skip through, you know, it takes like 5 minutes. If you do it over and over again, that adds up. So this allows us to skip through all that stuff. Go through that again. Anybody have any issues with that? Okay. Alright, you guys keep going. So do it from there. Find where it's concave up, concave down, and if there's any points of inflection. We also skipped the HAVA part, which does matter. This one, why does it matter? It's fractions. Do that part too. So, are there any horizontal asymptotes? Somebody speak besides me. No, why not? High bars on top. So no horizontal asymptotes. Are there any vertical asymptotes? Yes, because vertical asymptotes from the bottom equals 0, so there is a vertical asymptote with s equals 0, which is at x equals 2, right? Okay. So at the top equals 0, 4 equals 0, never happens. So at the bottom equals 0, when you solve that, you're going to get x equals 2. Gives you your number line, negative infinity to 2. 2 to infinity. Pick a point in this region, so let's say 0, and plug back into which level? Second derivative. Plug it back into the level that you came from. So if I plug 0 in here, 0 minus 2 is a negative number. Negative number to the third power is still a negative number. Positive divided by a negative is still a negative number, so my second derivative is negative, which means my original is concave down. Repeat that with something between 2 and infinity. 4. 4 minus 2 is positive. Cubed is still positive. 4 divided by positive is still positive. So the second derivative is positive in this range, which means f is concave up. So at this point, you might think there's a point of inflection. There's not. I'll show you why. Do you see why I'm saying there could be? You're switching from out to up, right? So then your next step would be typically, okay, I'm going to say, yeah, there's a point of inflection, great. It's at 2, comma. But I go plug back in. Well, when I go plug back in, I get 4 over 0, which should remind me 2 can't be a point of inflection because it's already too busy being what else? It's already a vertical asymptote. So a point of inflection has to be like an actual dot that goes on your graph. And you can't have a dot like where there's an asymptote, you know? So there's not a point of inflection in this one. And you just have like these 2 spots. It's got to give up here, it's got to give down here. There's not a single point where that changes. So this one, I don't know exactly what it was. Let's grab it. Concave down here, like that, and then concave up here. So there's not a single point where that like switch happens. It happens around an asymptote. There's like a wall there. How many had that? How many had like the majority of that? You're picking up what I'm putting down a little bit. Alright. Questions for me at all? This is your homework. Since we just did, I tried to go through one of all the types there were. See that.